Hello, everyone. Welcome to my talk. Today, I'm going to talk about how we use Databricks to manage millions of tests inside Databricks. First, let me introduce myself. My name is Yin Huai. I'm a staff software engineer at Databricks in our runtime group. During my early days at Databricks, my work was primarily on Spark SQL. In the past 3 years, I've been focusing on designing and building Databricks runtime container environment and its associated testing and release infrastructure. Databricks operates a global scale and multi-cloud data platform. Our platform control plane is deployed to different cloud regions in order to support our thousands of customers around the world. In Databricks, we maintain a deep technical stack with various systems to power our data platform and keep iterating our data platform at a fastest pace. To scale efficiently in terms of both providing more values to our customers and helping us sustain the increasing load, we have been keep investing into the factory that builds our data platform. In this factory, we build out a cloud abstraction layer for key integrations with cloud providers. This layer, Kubernetes and Docker combined, provide a cloud agnostic environment for developing and operating services powering our data platform. There are also a set of foundational services. They provide common functionalities like monitoring, access control, and billing to other services in our platform. Then at the top of our stack, there is a layer of services that handle various of operations initiated by our customer. And there is a Databricks Runtime, which provides standardized computing environments to all clusters powering customers' workload. Besides having a deep technical stack, Databricks Unified Data Platform has a wide surface area to our customers. With Databricks Runtime, customers build different kinds of workloads using SQL, Python, Scala, and R. The entire Databricks Runtime cluster is presented to our customers. They can build workloads from accessing functionalities provided by the operating system to just use high-level declarative languages like SQL. Also, with services like Job Scheduler, SQL Analytics, and MLflow, Databricks allow our different types of customer to work on different types of data problems on a single unified platform. Today, there are millions of Databricks Runtime clusters running. Our customers use Databricks Runtime to solve different kinds of data problems in various domains. As you can tell, our data platform is a complex system, and there are lots of different functionalities that our customers can use to power their mission-critical workloads. The quality of our platform is crucial to the success of our customers. In order to ensure the quality of our system and improve the quality, testing is key. Inside Databricks, we are testing our system at a decent scale. The graph here shows the average total test execution time per day for each week since October 2020. We now run 2.8 years of tests each day. There are 54 million tests running per day, or 630 tests per second. The volume has more than doubled in just a little bit more than 6 months. There have been several challenges on our path to run tests at this scale. First, we need to execute tests at a scale. Taking Databricks Runtime as an example, we have more than 150 CI jobs and thousands of CI job runs per day to test all versions of the Databricks Runtime. While running a high number of jobs frequently, we often hit scalability issues with Jenkins. To be able to execute tests at scale, we have been building an in-house CI system and gradually migrate CI jobs to that. As we have the new CI system that helps us execute tests at scale, we also need to be able to dispatch CI jobs at scale, as we're using a monorepo and the loads on pre-commit CI testing is high. To address this issue, we built GitHub webhook receiver and consumer to dispatch CI jobs at scale. With the growth of our business, we are going to write and execute more and more tests. We need to be able to handle test results at scale. Even the event of a single test failure is very rare, Since we run a large number of tests, and there are tests that depend on external systems like cloud provider, there will be test failures every day. Let's do some simplified estimation. When a test fails once a million times, we will have 54 failures per day. If a test fails once in every 100,000 times, we will have more than 500 test failures per day. As we keep offering new functionalities and services to our customers, the number of tests will keep increasing. We will need to figure out a sustainable approach to keep tracking the results of tests we run. To tackle this challenge, we need a system that automatically triages test failures to the right owner in a developer-friendly form. To help us design this system, we firstly established 3 guiding principles. First, the system should detect and report test failures automatically. If any step requires human intervention, this system will not be able to produce consistent results, as different persons may handle the same task with different standards. Also, we will not be able to scale the system with the scale of the problem if we have human in the loop. Second, this system needs to connect the problem with the right owner. Every task should have an owner, but when a task fails, it's not necessarily the owner who needs to take actions. For example, when we run an integration test, it's possible it failed because the dependent service doesn't work. If we always triage the test failure to the task owner, we may frequently direct noise to the task owner. When the signal to noise ratio is low, the system and the reports created by it will quickly lose the trust of engineers. Then those reports will become useless because engineers will not treat those seriously or simply ignore them. In order to have a system that works in practice, this system needs to understand the failure and triage different types of failure to the right owner. Once we can connect the problems with the right owner, we also need to make sure the owner understands what is happening and how to start the investigation when they see the reports. In Databricks, we use Jira to track issues. So we need to ensure reported Jira tickets are well organized and information surfaced through Jira tickets do not overwhelm our engineers. So our engineers can know the number of unique issues at high level and also know how to get more information to debug problems. Finally, it's possible the failure attribution needs update. We also want to empower our engineers to make corrections in a self-service way. In the rest of this talk, I will show you how we build a test failure reporting system. I will first explain how we approach the problem. Then I will give you a system overview to help you understand how this system is implemented. First, let's see what is the problem we need to solve. For a problem, we need to collect data from 3 sources. We need to get results, test results from Jenkins and our in-house CS system. Also, we need to establish the mapping from test to test owner. Since we use Bazel as the build tool inside the Databricks, we will need to figure out how we get the owner information for each test target defined in Bazel. Then, with test results and the mapping from test to test owner, we need to generate test failure reports and send them to the issue tracking system. We need to generate test failure reports that fit the abstraction of Jira tickets with owner attribution surfaced through setting Jira components. As you can see here, we're essentially looking at a data problem that requires 3 kinds of data pipelines to solve. The first data pipeline is used to collect test results from CI systems. The second data pipeline is used to establish the test to owner mapping. For both pipelines, we need to persist the data in a form that later we can use to generate failure reports. The last data pipeline is to use persist data from previous 2 pipelines and direct failure to Jira as the destination. Now, as it's clear what we need to do, let's see how we get everything implemented. To implement those 3 pipelines, we need to first pick the right tools. There are 3 key decisions to make. First, we need to determine where to host the data pipelines. As the problem is how to design and implement data pipelines, there is no better place than Databricks to use. Databricks allow us to easily manage our data pipelines and use rich functionalities to analyze data. Second, we need to figure out how to access CI systems results and Bazel build metadata in Databricks. Because we're using Databricks to host our data pipeline, we're using Databricks Runtime to process our data. So we'll use Spark's data source API here. And finally, we need to decide how we store CI systems results and Bazel build metadata in Databricks. As we're using Databricks, this decision is also easy to make. We use Delta to store datasets. Delta makes continuous data ingestion simple, which I will talk about it more very soon. So now we have got our tools picked. We're ready to look into our data pipelines. First, we look at how we build data pipelines to establish test results table. For our in-house CI system, we simply use Spark's JDBC connector to load data directly from our CI systems database. For Jenkins, we build a Spark Jenkins connector to allow us query Jenkins build and test data using SQL and a data frame API. This data source exposes Jenkins data through 3 views. The jobs view allow you to query available Jenkins jobs. The builds will allow you to access the build level metadata like build status, build start time, and build parameters. The test will allow you to query detailed test results of selected builds exposed by Jenkins JUnit plugin. Through this build, you will be able to see things like error messages and sectors. As we can load our CI systems data now, we can keep building the data pipeline. So Delta is the destination table format. Using Delta here makes building the continuous data ingestion pipeline easy. When accessing Jenkins, we cannot simply ask Jenkins to return build finished after a given timestamp. So we need to query Jenkins to give us most recent builds. Then we use merge into to only insert new records to the test results table. Also, when we build the data pipelines, the test results are partitioned by different jobs. So we take advantage of the transactional support of Delta to have parallel data pipelines running to ingest data from different Jenkins jobs to the single destination table. And finally, in case any bad write happens, we can use Delta time travel to roll back to a recent version and refill the data. Now, after checking out the pipelines that ingest data from CI systems, let's check out how we collect tests to owner mapping. In Databricks, we use Bazel, which is a powerful and highly customizable build tools. Bazel allows us to see the metadata associated with any build target. For example, here is the example output of metadata associated with the build target myTest inside package foobar. Through this XML output, we can see that the build target is a Scala test target because this target's class is generic Scala test. This target will execute the suite com.databricks.myTest. Also, the most relevant field for what we're talking about right now is the owner's field. It says owner is a Spark M, which is a team name, which is my team's name. As Bazel can return this structured information for every build target, we will be able to regularly query Bazel and populate a table that maps tests to their owners. This diagram shows the current process of populating the test owner Delta table. Once the data pipeline starts, they first check out needed repositories, then it will issue Bazel queries to get XML output of build targets. With those build target definitions, we'll parse XML record and convert them to a Spark data frame. Finally, we write the data to data table. If there is any existing record, we'll use the record from the latest development branch to update them. If there's no existing record, we simply insert the new records. For the task owner table, every record shows the task suite name and its corresponding Jira component of the owner. Since we use Jira to track issues, the team name we saw in the previous slide was simply a pointer for us to find the actual Jira component. With this task to owner records, we will be able to tell who owns the task. In case we need other fields from Bazel build definitions, we can easily adjust this pipeline to include those new fields. Finally, let's look at how we consume task results data and task to owner mappings to report task failure to Jira. From task results to Jira failure reports, there are 3 steps. We first build a failure detector whose job is to query task results table and load task failures that we want to monitor. Then this failure detector has interested task failures to task failure analyzer, whose job is to analyze failures to determine the type of failure. The type of failure will later influence how we report a failure to Jira. I will talk more about why we need this analyzer very soon. Finally, analyze the failures will get passed to a failure reporter. Failure reporter will turn the analyzed failure to our internal abstraction of a Jira ticket based on the failure type with the guide of a task owners table. Then failure reporter will send the reports to Jira. And here, you'll probably have a question about how we know what failures have been reported. For this data pipeline, we have 2 mechanisms to help us avoid sending duplicates. First, when we report a task failure to Jira, we will query Jira to see whether the same task suite of the same build has been reported. However, it's not efficient to frequently query Jira. Also, for analytics purpose, we need a mechanism to allow us to query what got reported to where. So we added task failure reports log table. After we send all reports of a failed build to Jira, we'll log which tickets a task suite of this build got reported to. With this table, failure detector will be able to filter out suites that have been reported. In a rare case, when the pipeline failed before we write out the logs, the previous mechanism will still check Jira and allow us to avoid duplicate records. So now we have talked a lot on how we build out the automated data pipelines based on our first guiding principle. Let's look at how we report failures to Jira following our second and third guiding principle. So the second guiding principle is to connecting the problem with the right owner. Although we have task to owner mapping, we cannot fully rely on them to determine who should receive a failure report. Actually, it's quite common that task owner is not the owner of certain problems. In order to direct the task failure to the right owner, we need to understand types of failures and how we should determine the owner of the failure for each type. The first type of failure are problems caused by testing environment issues. For example, an integration task that needs to launch a cluster failed to launch the cluster. For this type, sending the failure to the task owner doesn't help. Because task owners are often not the owner of the testing environment, instead, we need to find the owner of the problem. The second type of failure are those failures caused by other task failures. You will see this type of failure when tasks are not running in isolated environments. For example, one integration task somehow changed the required data set used by another integration task. For this type of failures, because they are not the root cause, they're just noise and we don't need to look at them. The last type of failure are failures that do not belong to type 1 or 2. For those, the owner of the task should own the failure. In our failure analyzer, we'll determine the type of a task failure based on the pattern in error messages and set traces. Then we'll send failure in different types to the failure reporter. For type 1 failure, we'll also attach the owner of the problem, as we'll not look at the owner of the task. Now we have all relevant information available, we need to organize the information in a developer-friendly way, so developers can consume them efficiently. In order to determine how we should organize different type of failures, different type of information, we will need to look at how people will use those reports. In Databricks, we primarily have two use cases. The first use case is that we need to understand unique problems associated to a given team for a given time window. When engineers are on call, they need to get this high-level view to know what is going on and pick where to start. Also, when we regularly review how we are operating, we want to see stats related to test failures for teams for a given time window. The second use case is that when we start to debug a specific problem, we want to know more details to help us investigate the problem. So common questions are how test failed, what test environment is having problems, and when the test failed. So basically, we need to have a detailed view to be able to see all relevant information to help us quickly figure out the root cause. To serve these two use cases, we need to present test reports in Jira at two levels. First, so we'll use a two-layer reporting structure. We first create parent Jira tickets to represent a unique problem. These parent tickets will group all failed instances of the same problem together. Then we'll create subtasks to represent individual failures happening in a specific test environment. With this two-layer structure, any new failed instance will get reported as a comment in the right open parent ticket and subtask. Let's see two examples. For an example type 1 issue, that cloud provider cannot launch virtual machines because we exceeded the virtual machine quota, we will group all kinds of failed instance type, no matter what test suites are failing and what versions are having this failure. For example, type 3 issue, we will group failed instance of the same test suites. Here is a full bar suite from different testing environment and Databricks Runtime version together. So here, I also want to point out that the two-layer reporting structure essentially allow us to group failures at two levels, and we can adjust how we want to group them as appropriate. For example, for type 1 failures, if we find that parent tickets should only group failures in a single testing environment together, we can easily make the change. Of course, developer-friendly failure reporting is not just about how we group failures. We also need to take advantage of features provided by the issue tracking system. As we use Jira to track issues and track release blockers, we have an automation to automatically escalate failure that match certain criteria to blockers. We also automatically set effect version to test failure reports. So critical test failure can find its way to our release blocker dashboard, and test will see and team will see what test failure should get handled first. Finally, developer-friendly failure reporting is also about how to make developers to easily fix any owner attribution issue or any problems related to determining the type of problem or failure. In Databricks, developers can fix this issue easily by submitting a small code change. Once the change is reviewed and merged, it will get automatically deployed. Okay, those are all I'd like to talk about today. In summary, we talked about building automated data pipelines to manage test results at scale. Through my introduction of our data pipeline, I hope you'll see how Databricks and Data make the work easy to implement. We look at how we connect test problem to the right owner and why it's important. And finally, we discuss how we surface information from CI systems to Jira to make test failure reports easier to be consumed. We still have more to do in this area. In particular, we want to start to build a holistic view of all CI/CD activities. With the data we have from our CI/CD systems, we will be able to gain insights to continuously drive the improvements of engineering productivity, product quality, and operational efficiency. If you find our work on this area interesting and you want to get hands-on experience on it, I hope you can join us. Thank you everyone for your time. Have a great day and enjoy this year's summit.